Morning and good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Peter Ture from Business Review, and I'll be your host today. It is our pleasure to have with us PROMECON, who will be presenting us on the topic titled Mill Mass Flow for the Dynamic Control of PF-fired Boilers. You can control what you can measure properly. Now, today's guest speaker with us would be Hans, who is the CEO and President for PROMECON. I'd like to welcome everyone here to On24. You notice that this platform is browser-based, so if you do disconnect for any reason whatsoever, please click on the link that you received via email to rejoin the session. In order to ask questions, you can send them in via the questions widget. Just type them into the box at the top right-hand corner of your screen and click submit. We'll then allocate some time at the end of the session to address any thoughts or questions that you may have. Please also use the yellow help widget in case you need any assistance to move, resize, and maximize any of the screens in front of you to help get a better view of today's session. But for now, please allow me to hand you over to our speaker of the day. Hans, over to you.
Thank you very much, Peter. I'm very happy to be here today to talk about combustion control. And today we are going into a fairly advanced field because it has a lot to do also with boiler and load control. Our company has been active in the field of thermal process and combustion control for over 26 years. And one big field of our business, besides smelter business and cement business and waste incineration, is the power business, and especially the control of PF-fired boilers. Now, PF-fired boilers can be coal-fired boilers. It can be also biomass-fired boilers. Right? So as long as it's solid fuel, we have been looking at controlling the boiler and the combustion. Now, not long ago, we had another webinar on this channel, and I was talking about combustion optimization. So we were talking about bringing the coal and the air together at the right air-to-fuel ratio in order to optimize combustion for NOx, for CO, and for other hazardous constituents of the flue gas that you would like to minimize. So the question back then was how to use our technology in order to have a better flame, a more stable combustion. Today, we're talking about a completely different thing. Today, we're talking about dynamics. Dynamics in load and dynamics in mill operation. Now, as the audience will all be power engineers and power people, you know, of course, that you have a long chain of events before the coal that comes out of your bunker finally turns into megawatts on the turbine shaft into the generator. And this chain is a long succession of energy release. And the biggest bottleneck in this whole chain is the pulverizer. So let's start again with pulverizer, the focus of so much measurement of PROMECON in the past. I will show you a picture that illustrates this. Here you can see the start of a pulverizer. And on the top half of the picture, you can see the fuel mass flow that comes out of the pulverizer. Yeah? Now, when you switch something on, of course, you flick the switch, it goes from 0 to 1. And as you can easily see, the pulverizer does not go from 0 to full load, but there is a long transition period in which the pulverizer increases its output gradually and slowly. Not surprising, you all know this, the pulverizer has a certain circulation of coal, so not all the coal that leaves the roller table will exit the pulverizer. Much of the coal falls back, will be ground a second time, sometimes even a third time, before it leaves the pulverizer. So any step change with the feeder you make has a delayed response in the pulverizer. Let me show you this in another picture. Here we have a very nice illustration of that. One graph is the feeder. That is the solid line. That's the feeder starting. Yeah, that's a typical pulverizer start from 0 to 6.5 kilograms per second. And you can see the dotted line. This is what the PROMECON device measures out of the mill. And as you can see, there is a huge delay. And especially at the transition period, I mean, look at minute number 2.5. After 2.5 minutes, the pulverizer feeder has nearly reached its maximum, but the output of the pulverizer is far away from that. So pulverizers have a long response time, and in the whole chain of events, from feeder to turbine shaft, the pulverizer has the longest lead time and the most variable lead time. So as long as you run your unit flatlined, one load is no problem. But we will see in the future, many coal-fired power stations of this world will not run on steady load. They will be running up and down in load to accommodate the changes that come from renewable energies. And in this case, it will be very hard to control them because the change in the coal feed to the pulverizer is released as combustion energy minutes later in the boiler, and nobody really knows exactly when that's happening. And that is our main theme today of today's discussion. And the second theme I'm going to talk about is a better pulverizer control in itself, which is also a matter of better controls. So let's start. To start with, let's look at a pulverizer. Yeah, I mean, this is a very simplistic view of a pulverizer. You have this big gray box. The big gray box has a feeder on the top in green that throws in the coal. Then the coal falls into the pulverizer to the grinding table. Then you have the primary air that also comes in from the other side and that pushes the coal out through the pulverized fuel lines. Now it all starts with the measurement. If you do not measure the output of the mill, you have no chance to optimize any of it because you don't know when the coal is coming out. For this, we have developed a measurement system that I have talked about last time. And for all the people that may not have seen my presentation last time, I will repeat how we measure coal flow briefly. So we're all on the same page as to the measurement technology. So we have sensors on each of these coal pipes. And our measurement system is capable of measuring the coal mass flow out of each coal pipe. So in each coal pipe, we have a coal flow consisting out of a certain coal concentration and a certain coal velocity. And the concentration times the velocity is the coal mass flow. So this is what our system is measuring. So let's look at this. The coal flow system consists out of a main central panel, out of a local field box that can measure a certain amount of pipes. Let's say 4 pipes, that would be 1 mill, sometimes 5 or 6 pipes. Then the sensors that are connected to this measurement box, and also the temperature sensor and the reflector rods that are put into the individual pipes, and of course the cable that connect everything. So this is basically the toolkit that you need to measure 1 mill, 2 mills, the complete set of mills in order to optimize your boiler. How does the system really function? How is it measuring? Our system has 2 distinct types of measurements that are incorporated. The first one is a so-called microwave measurement. The microwave measurement allows you to measure the coal concentration in the pipe. The second measurement that we have inside our measurement system is a measurement of coal velocity. And this is done with an electrostatic charge measurement that is then correlated between 2 sensors. Briefly explain principle number 1, coal concentration. We use this pipe as a resonator. So we put in a microwave that is reflected on these reflector rods that you can see. So it's creating a standing wave, and you have a certain frequency at which you have your resonance. So you sweep a certain frequency range, and at one frequency you can see, this is my resonance frequency. I have a very big response that I can measure on the receiving antenna. If you are now adding coal into the pipe, or biomass dust, or any other fuel, that resonance frequency will go down to slightly lower frequencies. So So the change in resonance frequency is directly proportional to the amount of concentration of material in that pipe. You double the concentration, you double the frequency shift. You triple the concentration, you triple the frequency shift. So you can see which pipe has a high loading and which one has a low loading. Of course, we also need to know how fast is the material flowing through the pipe. And this we do with what we call electrostatic correlation measurement. Now we have two sensors that I've explained to you before. We use them for microwaves. These two sensors we are also using for the electrostatic measurement. But now with a different principle. We are looking at the electrostatic charge of sensor 1 and sensor 2. And we can see a certain electrostatic charge on each sensor. Now, if you imagine you have certain clouds of particles that are flying through the pipe, they leave a certain signature on the first sensor, a certain, let's say, time signature, a certain pattern. Now, this pattern repeats on the second sensor, which is only this very close to the first one, only 500 millimeters away, or 300 millimeters away. So that pattern is repeating on the second sensor, but it's time shifted. So you have the two patterns. You can see them in the original picture here, sensor 1 and sensor 2. You put the two patterns on top of each other, and then you do a cross correlation. You shift them, and you see at which time shift do they have the best match. And the correlation function that you can see on the lower right hand has a sharp maximum at the point in time with the highest match. So we get a time shift. We know how fast the cloud of particle goes from sensor 1 to sensor 2. So we know the distance, we divide by time, meters per second, we have velocity. This is basically it. We measure the microwaves concentration, we measure the cross-correlation velocity, we multiply the two, and as a result, we get the mass flow of the system. And the mass flow is the thing that we want to look at today. The mass flow today is our main objective. What can we do by knowing the mass flow out of the mill? Let's have a look. First of all, here you can see a picture of a typical measurement. On the bottom you can see the velocity out of the mill, transport velocity. Last time I mentioned how important transport velocity is in order to avoid pulsations and other problems and deposits. This time we're really focusing on mass flow, and the top you can see the mass flow. And again, when you look very closely, when the mill starts on the left hand side of the picture, can you see the velocities coming up like flicking on a switch, instantaneous on the lower picture? And on the higher picture, the mass flow is not coming on instantaneous. It takes some time. It has a certain incline. There is a certain time delay before the mill really puts out the coal. So this gets me to the first big part of the session. What can you do with this? And I would like to give you the situation in Germany. Typical for Germany is the big portion of renewable energy that we have in our grid. And wherever you are in the world and listening, there are still markets where you have lots of coal and not many renewables. But be aware, I think globally, renewables will take a bigger portion of the electrification or electric production. And the bigger the portion is, the more destabilized the grid will become. Yeah? If you have a grid with 100% coal or gas or whatever, and you add 5% renewables, not much is happening. If you increase from 5% to 10%, you will see some fluctuations in the grid. Why? Because sometimes the wind is blowing, sometimes the wind is not blowing. Sometimes the sun is shining, sometimes it's not shining, and there can be very abrupt changes between the wind blowing and the wind not blowing. So if you increase the amount of renewables in the grid and you push down the conventional, your grid will be more and more destabilized. And this picture you can see here, this is the power in megawatts. That's already over 10 years ago in the German grid. It has become even worse. You can see now up to 20,000 megawatts coming on and off from one day to the other. Between night and day, there's always certain fluctuation, but even hourly fluctuation, minute fluctuation increases. So now people have to compensate this by their coal plant. And you can't compensate this by letting your coal plant run flat-lined. You have to run your coal plant exactly opposite, so that the output is still constant and still meeting the demand curve. That's the challenge. You have to make out of your plant your plant is a large ship, a huge tanker, and you have to make it a racing car. How do you do that? How do you change this? And when you look at this, you have to look at the time delay, the dynamic behavior of your plant. And this has a lot to do with your pulverizer. So let's look at this. Again, the picture that you've seen before, you start the feeder, but of course, the output of the mill is not there, right? Every control engineer knows this. In every control system of a power station, you have PT elements in your controls that have a certain time delay, right? So every Siemens, ABB, or whatever Foxborough control system has these elements. So when you turn on the feeder, the control system will have a feed-forward control to the feed water pump with some time delay, because there's some time delay here, right? Now, what you want to do, however, you want to accelerate this. You want to have a faster primary frequency control. You want to have a faster secondary frequency control, and of course, a higher load flexibility. How do you do that? Well, the big thing here is, of course, you have certain reservoirs of energy in your power station, right? You have the coal that becomes combusted fuel. And then, of course, you have the enthalpy of your boiler, your steam. Then, of course, you also have the condensate that comes down from the turbine. And you have the preheaters, the low pressure and the high pressure preheaters. So there are a lot of points where you can suck out energy, where you can delay reheating in order to ramp up the load. And the only thing that is important is you have to know when the coal will really come out of the mill in order to support your load gradient. If you go into a steep load gradient by, for example, slowing down the condensate pump, you have about 50 seconds that you can suck out the enthalpy of this process. And after 50 seconds, you have to be sure the mill can deliver what it needs to deliver in 50 seconds, because otherwise you become unstable and you get load swings. I'm going to show you that in a minute. What you can see here is what I've described earlier. You have the input to your feeder, yeah, so the load input. And then, of course, you have a main controller, and that changes the feeder. And then, of course, you have a certain time delay before you can change your feed water pumps. Of course, there are a lot of feedback loops that control temperature and pressure. So, everything is, of course, feedback controlled. But the feed-forward control needs some time delay. As you all know as mill engineers, the time delay of your mill is not constant. And that's the big problem. Sometimes you have a good coal that grinds fast. Sometimes you have a bad coal that takes a longer time to grind. So you can't say after 3 minutes my mill follows. Sometimes it follows after 2 minutes, or only after 1.5 minutes. But when will the mill really spit out the coal? No one really knows. And that is the point that we need to address. So what we are really doing to make the boiler faster is we want to have a real-time measurement of the fuel into the boiler. That means we have to measure between the mill and the boiler. Nobody is measuring on their online until we have this new online system installed for PROMECON. This is a new way of measuring coal mass flow. Of course, we then want to use this measurement for the modification of the mill controls for faster load swings, to ramp the mill up faster, for example, by using roller pressure or by using the primary air, yeah, and using to really push the coal out faster when you need the coal. Of course, we want to use it for much better synchronization between fuel heat release and feed water control, because you want to have lower boiler stress and you want to have a much better match between the heat release and the feed water. Then, of course, you can use the condensate pump controls for faster load gradients, right? All the condensate is preheated by steam. So if you have a load gradient, you can say, I'm not going to reheat my condensate because I have a reservoir of condensate. So I wait for that for a few seconds. And during that time, I'm using all of the steam to put it on the turbine as fast as possible. And if you do that and you have a cascaded control of your water-steam cycle and the fuel parameters, you can ramp up your unit much faster. We have demonstrated this in power stations in Germany and other places, and it is a very powerful tool to make your plant more dynamic. So the target is to obtain instant fuel flow rate and, of course, also to understand the dynamic properties of your pulverizer in order to increase the complete control chain up to your load control. So in very, very crude terms, what we are doing is we are looking at what goes into the mill. We are measuring what comes out of the mill. And we put this into an observer, basically a state controller. And this state controller automatically adjusts the transfer function of the mill. Transfer function means how fast is an impulse that's going into the mill coming out of the mill. And that transfer function is essential then to control feed-forward parameters such as feed water. So usually what happens if you control this by an advanced state controller, you have a reference model, you have an observer, and the reference model will continuously be adjusted to the transfer function that you see on the mill. And this allows you then to really predict when the coal will come out of the mill by using the state controller, and you will use the online flow measurement continuously in order to control, in order to correct that observer and the reference model. Just a little bit more detail on that. I hope it's not too theoretical, but in the real world, it's very, very powerful. Let's look at this very simplistic model again of the advanced mill controller. On the left-hand side, you got this mass coming in from the feeder, the M.RC. This is the mass flow that's coming from basically the feeder belt from the bunker into the mill. On the top right-hand side, you can see this variable ZPF. This is the measurement that comes from the PROMECON measurement, really saying this is the amount of coal that is coming out of the mill. Now, what this model is doing, it's first of all comparing the two, but it also does another very important thing. It looks at the constant and the dynamic value of both inputs. And you can use this model in order to value the dynamic and the constant value independently, right? So the output, which is at the lower right hand, you see the MPF with this little line on the top. The MPF is what the mill gives out, the mill controller model gives out as the actual value that's coming out of the mill as a prediction. And the feeder is really used as a dominant static value, whereas the PROMECON value is used as the main dynamic value. And this is very, very important. So you still need the feeder in order to tell you how many tons are going through my mill. But the dynamic value of the PROMECON system will tell you how much of that, how many percent of that is now exiting the mill, and how will that affect the true flow to the burner. So again, let's summarize. You have state variables that can be measured. You can measure the feeder, you can measure the mill, the furnace, steam generator, turbine. Between the mill and the furnace, usually in a power station, there is no state variable. But now we have a new state variable. We can say the transfer function between feeder, mill inlet, and outlet. And this allows you to optimize the whole chain of events from the feeder input to the turbine generator output, because all the other time variables are very small. Let's look at this. You have a control. This is very complex. I'm not going to bother you too much with this, but you have a very complex control algorithm for your boiler. This is really controlling the boiler by feeder. And what we are doing now is we are adding a second branch where we give a second input to controlling the condensate and also the feed water pump in order to accommodate for the corrected fuel flow measurement to the boiler and have a much better feed forward target when ramping the boiler up and ramping it down. What does that help? That helps a lot in making the transition smoother, in making it possible to have a steeper transition from low load to high load and back. There's no more effective way than measuring the cold flow in order to optimize and speed up the control of your boiler. So you have a parallel controller, a branch that can be switched on and off, bump free, of course. You can switch this control feature on and off. So you can run the boiler as you have been running it before, but you can also enhance it in its dynamics by using our measurement. Let me skip that. Let me just show you what the outcome is here. You still remember the boiler, the mill control model, the feeder in, and then below the cold flow in, and then the optimum, the estimate of the model. And if you see those three lines, you can see the feeder dynamically is very, very wrong. However, when the feeder runs steady state, we just take the feeder value as the main value to lead the combustion control. The PROMECON measurement in the dynamic transition is far more accurate when it comes to what goes out of the mill. So if what comes out as the estimate is really this dotted line that you can see here, that is following the PROMECON measurement very well in dynamic phase, and when it goes to steady state, it's following the feeder very well. So you can use this measurement to directly control the boiler. We've done this in many applications, and it shows that the whole process is running much better than before. Just an example here. We did a toggle test. We switched the controller with the PROMECON on and off. And when it's off, you can see on this pink line, the current controller, the reaction to a load change is far slower than with the enhanced state controller using the PROMECON flow measurement. We had nearly 3 times earlier reaction of the whole unit to ramp up and ramp down, and 3 times in a load jump. 3 minutes is a long, long time. This has been published in a paper by Uniper Technologies in 2017 PowerGen. If you want to have this paper, just write us an email. We were going to show you what we have presented. We got a best paper award for this work in enhancing coal-fired stations for faster load change. And here again, an example, we toggle back and forth. One day we did not use our controller, and you can see the blue line is the set point up, you're going down and up again. And then the red and the other line, the blue line and the purple line, this is how the pressure and the power is following. So this is without an enhanced control, and this is with an enhanced control, right? So if you go back and toggle out, you have this. And if you use the coal measurement with enhanced control, you have that measurement, or you have that outcome. You have a much more smooth transition in high load changes. So this was how to optimize a complete boiler with our PROMECON measurement and a controller. I would like to show you now a second example. This helps you to control the mill behavior by itself. How can you make a mill behave better than now? And many power plants have, whether they're using coal or biomass, they have fairly big problems to control their mill dynamics by itself. And I would like to give a few examples of how we have optimized mill output by our measurement system. Again, here, the basis is a state controller. So you have a big controller. And now let's look at the parameters that we use to optimize the mill itself. We are taking, in this mill controller, we are taking in the PF demand from the power station, the mill DP, the mill outlet temperature, and we are taking in the measurements. I mean, these are all the set points. So we have the PF demand set point, the mill DP set point, mill outlet set point, etc. And then, of course, we're taking the actual value, the mill DP, the outlet inlet temperature, the feeder speed, and, of course, the cold flow that we measure out of the mill and the PA flow that we measure into the mill. And then on the outlet, we have the feeder speed demand. This really tells the mill what the feeder should do. So this controller is not only looking at something, it's making a change in the mill controls. It's also giving out a PA demand signal. It's giving out a cold air damper demand and a real-time PF flow estimate. So with this controller, you can tell the mill what to do. You can control also the internal masses of the mill. You can control the level in the mill. You can control how fast the mill should ramp up or ramp down, of course, within the limits of the mill operational envelope. So here we have an actual picture of such a controller. And let me explain the individual points. The more interesting part is on the bottom of the picture. You have actually the dark blue line, which is basically the PF flow demand. This is what I say. This is the demand of the PF flow. Yeah. So the boiler overall controller wants such a certain fuel demand, and then you have the feeder flow demand. So, you know, the PF flow demand is a signal of how much coal you want to have in your boiler. The feeder flow demand signal is that purple line. And then you can see this light green line, which is very, very noisy. That's the PROMECON measurement. That's the real-time measurement of the coal or the PF that's coming out of the mill, or the biomass that's coming out of the mill. Biomass is a big, big issue when controlling mills properly. Now, when you see this signal, many people from Siemens and ABB have told us, this signal is so noisy, I cannot control anything with the signal. But the signal is so noisy because the mill is pulsating. Yeah? This signal is no artifact. It's a real pulsating signal out of the mill, but you can't use it to control the mill properly. Now, if you take this light green line or blue line and put it into a low-pass filter to smooth it out, the controls will become so slow that you can't use it either. But have a look at this red signal. This is the PF flow estimate signal that comes out of our controller. The PF flow estimate signal is what the controller makes out of the measurement of the PROMECON system and all the other inputs. It's calculating the transfer function of the mill, and the prediction of the PF flow estimate is really exactly inside the PROMECON measurement. But the dynamic changes that we see and all this very, very unsteady flow is smoothed out by the PF flow estimate. So this PF flow estimate value can be directly used to control your boiler. Let me show you what you can see here. For example, the feeder flow demand goes up, and of course the feeder flow goes up. You can see that purple line. And then, of course, the mill reacts much, much more slowly. The mill reaction is really with a big time delay. And this is exactly what you can see. Here I have another very nice from a mill model. Here's what's happening. You have 4 signals here as an example. You have the flow model estimate, you have the PF flow, the real PF flow, you have the feeder rate, and you have the mill output demand. Now, the output demand is a very simple line. It goes up in steps, so this is what you want to have out of the mill. And if you use our controller, you can have the actual PF flow and the PF flow estimate very, very tightly matched to the demand. we can help you to get the coal very, very close to the mill output demand. But look at what we have to do to the feeder. The feeder is overshooting. The green line is all over the place. So this is very important to understand. In order to have a smooth output from the mill that you want for your controls, the feeder has to jump up and down. The feeder has to do all sorts of things in controls. So the feeder cannot be controlled in the same way that you want your output. The feeder has to be controlled in a much different way so that your output reaches the target properly. And this transfer function is provided dynamically, accurately by our mill model. Have a look at this. This is real data from a plant in Denmark. It was part of a big paper that was presented. The people in that power station, they took our online measurement and also a state controller in order to predict the real output of a mill. And they then did the following things. They said we have the problem when we change mills, when we take one mill out and put another mill in. It should be done in a way that the transition is nearly constant, right? So whatever you take out should be put in, so the total mass flow, the energy release in the boiler does not change. We want to have the same energy release. Now, what they noticed is when they take one mill out and the other mill in, there's a huge disruption in the boiler heat release. You can see that on the evaporator outlet. You can see the evaporator outlet temperatures have huge disruptions. So then they used our controller, our measurement, and you can see the two examples here. You have the solid line, mill 7 was taken out, mill 8 was put in. So you have the solid line without correction of the model, yeah, and then you have the dotted line with correction. You can see how fast the mill is pulled back because all of a sudden the new mill comes in, and as the new mill comes in, there's a huge amount of coal coming out of the mill, and you have to correct for that so that both mills, in sum, both mills together, always have the same amount that they put into the boiler. And you can see the result in the evaporator outlet temperature. Here, on the left-hand side, this is with our correction. You can see the temperatures are much more smooth. And on the right-hand side, you can see without correction, because the mills are not corrected properly, there's a far bigger fluctuation in the boiler heat release. So you can make mills behave far more predictable. You can make mills work far more like a gas burner or an oil burner. And you can take out the element of surprise. When will the coal come out of the mill? Depends on the coal, depends on the biomass, depends on your fuel, depends on your mill. Yeah, if you have a worn out mill with worn out tires, how do you do this? If you have a state controller, you can control the airflow, you can control the feeder, you can control the roller pressure. The roller pressure is a big, big tool to make the coal come out of the mill fast or slow. If you increase roller pressure, the coal will immediately go out. If you release it, the mill will store in more coal. So you can use the mill as a buffer in order to have the output as constant and as predictable as you want it. Let me show you some more results of that. Here we have a mill that grinds PF. What I would like you to focus on is, again, the lower hand side of the mill. There are two effects that you can see here, which are very interesting. The first one is, on the left-hand side, you can see the line, you can see the writing MPC on. This is a mill controller that has been switched on. This is when the PROMECON controller becomes active. And then on the right-hand side, you can see the MPC off. This is when it's switched off. So what you can see here is that the PA flow and demand drops with the controller switched on. That's very interesting because we have not changed anything on the mill output. The same amount of coal comes out of the mill, and it comes out of the mill much more smoothly. But still, we were able to reduce the airflow to the mill. Very, very big effect. And in the lower graph, you can see the red line. When the MPC, when the controller is switched on, the output of the mill becomes far more flatline. It is not so dynamic anymore. It is a much better output with far less fluctuation. You know? And the most interesting point for me was the feeder, which is the green line. You can see on the right-hand side at the lowest graphs, when the controller is switched off, the feeder is completely flatlined. But the output of the mill becomes far worse. It becomes far more dynamic. And this is exactly the thing. You know, people believe when they have a flat feeder to the mill, the output of the mill is very, very flatlined. It's also very smooth. But that's not the case. When you switch our controller on, the feeder starts to move and the output becomes far more stable. Yeah. That's a very, very important point in stabilizing mills. Let me show you this in a graph. On the left-hand side of the picture, I mean, you have two lines here. One is the orange line, which is the feeder, and one is the blue line, which is the mill output. Yeah? And both is at constant load, no change. So before we switch our controller on, the feeder controls the input. Right? So the feeder is controlled. The feeder to the mill is the control parameter. So the feeder is flatlined, and the output is fairly noisy. When we now switch the controller on, the feeder will be moving back and forth, up and down, depending on the state that we can measure on the mill. And the output will become far more flatlined. Now, this is, of course, theoretical. This is just the model. What is the real data? The real data looks like this. Again, on the left-hand side, feeder control. There is no controller of PROMECON active. And you can see the output is all over the place. It's very dynamic, it's pulsating. And then the controller is switched on, and all the flows become far more flatlined, become far more stable. Right? So this helps you to cultivate your output. Why is this important? Let's jump back quickly to the presentation that I did a few months ago. If your mill is not constant in output, but your mill is pumping the coal like this all the time, how can you control your combustion? How can you control your NOx? How can you control your CO? The burner will always pulsate up and down. And this is what we see in many power stations in this world. We can see the output fluctuating, and the operators say, this is impossible. The feeder is completely constant. How can your output fluctuate? I don't think the measurement is correct. When we first installed our measurement with a controller, we could prove, switch it on. You can see everything becomes more stable, much more stable. So this is, of course, also a function that the bed depth of the mill is changing. And when the feeder is switched on, the bed depth is used in order to smooth out the output of the mill, and the output becomes much more predictable and much more flatline. So this is actually what we can do with this controller. Yeah? So we have mill stability. We can reduce coal output fluctuations especially in biomass. This is a very critical thing. We've done a lot of biomass projects in Scandinavia. We have a very big one in the UK, but we also did biomass measurements in other parts of Europe. And it's always a PA thing. You know, you need high PA velocities. We could prove that with a good controller, you can reduce PA velocities. You can use PA demand, PA air demand, and therefore also have a much better controllability of biomass-fed mills. You can increase load swing, yeah, and also you can make your mill more stable at low loads. Why is that important? Of course, minimum load, right? If you have so much renewable energy pushing into the grid, you don't want to take the coal power station out, but you want to run it as low as you can, keep it at a low level, because getting the power station offline getting the turbine cold and everything, that is a huge loss of money. So you want to run the boiler as low as you can. And what is the limitation for that? Of course, mill stability. The more stable you can make your mill, the less oil burners you need, and the better you can really cope low load generation periods. Okay, that's basically what I wanted to tell you. I hope you enjoyed this one. This certainly is a bit more rocket science than last time, because we're not looking at static imbalances. This time we looked at full boiler load swing of the complete unit. By the way, the unit you see on the picture here is the first boiler load swing unit where we did this with Uniper Technologies. Been very successful. And the second part I talked about was making your mills behave better, making them more consistent in fuel output and making them more predictable in changing mill load. So I hope that you have taken something out of this. I can imagine that there will be quite a few questions. We'll be happy to answer all of your questions. Any questions I cannot answer in this session now, we have only a few minutes to answer questions. We will take your questions. We will send you an email response, and we will certainly give you some more information on the work that we have done in tuning boilers dynamically to accommodate more renewable energy into the grid. Thank you very much, and I will be happy to take questions from you right now.
Yes, thank you very much, Hans. And just a quick reminder to the audience, in order to ask questions, you can send them in via the questions widget, type them into the box at the top right-hand corner of your screen and click submit. But for now, Hans, so have you used this technology to control a complete boiler in load?
Yes, actually the one that you see there on the screen is a very nice example. Another one that we have done in complete load was in Denmark, Asnæs power station. There have been a few ones that really have accommodated, especially in countries where you have a lot of renewable energy. And Germany has a lot of renewables. And of course, Denmark has many renewables and a very small fleet of boilers to accommodate for that. So yes, we have done that. It's a big task. It has to be done with the station together, with the controls people. But it has been successfully used to ramp up and stabilize boiler load swings.
Nice, okay. So, can you make pulverizers faster in their response to load changes with this controller, and how do you do that?
That's a tricky question, yeah, because of course our controller cannot do miracles. If you have a pulverizer that's limited in its dynamics, then of course you are limited in the load swing you can do. However, many pulverizers have an envelope that's much bigger than what you currently control. So you can make the pulverizer faster in many cases. And how do you do that? Well, let's go through it. What kind of parameters do you have? You have airflow, feeder, cold air damper, roller pressure. Dynamic classifier speed is another one. So you have a fewer ones. And to our experience, what are the most effective ones? I would say the biggest one is roller pressure. If you have a good roller pressure, dynamic roller pressure control, you can make the mill jump up and down and very, very quickly. You increase the roller pressure, and while the rollers push down on the coal, immediately there's more coal release, the grinding goes up very quickly. And if you pull it back, then the whole thing dies down quickly. Another support for that would be airflow. You would also have to, of course, accommodate the airflow that it carries all the coal out. And also classifier speed can help, but we have seen the big lever that you have is roller pressure. Of course, it means that you still have roller pressure left to work with. If your roller pressure is always maxed out, then you can't accommodate load jumps upwards, but you can accommodate load jumps downwards, which are also tricky. So that's how we do it. And I think everybody who knows mills and their plants knows roughly which direction I'm going. That's the way you do it.
Yes, thank you very much for that, Hans. Some very great insight. So, can you control the bed depth of coal on the roller table with this control device?
Yes, actually, we have been able to do so. The bed depth is usually a function, of course, of how much goes into the mill and how much flows out of the mill. Now, as I mentioned already, bed depth immediately is controlled by roller pressure, but also, of course, by airflow. If you increase airflow, even temperature, you will reduce the bed depth. Because you increase the drying capacity of the mill, and all these variables play together. So again, the state controller is able to not only estimate the flow out of the mill, but it can also estimate the internal masses of the mill. So we can, in one instance, in a biomass plant, we really had the target to increase or lower the bed depth in the mill, and we could do that. We could say as a target to increase the bed depth or lower it, and it can be done with not only with the delta pressure over the mill, but with all the state variables, including the flow that we measure. So yeah, you can even control parameters that you cannot see and you cannot directly measure in the mill.
Mm-hmm. Thanks for that, Hans. And for the final question, are there advantages to the combustion, such as NOx and CO, when using this technology?
Yes, in our experience, we have had lots of experience with mills that are not giving a constant output. Yeah, when you are operating a boiler and you have all the feeders going in a straight line, you think that the output of the mill is also constant. But the matter of fact is the output is always going up and down. There's no mill that's putting out the same output all the time. And that means that you have not only a variability in your flow to the burner, with a varying output, you also have a varying tendency of the coal pipes to settle coal. So there's coal settlement in the coal pipes, and this coal settlement will then push to the burner uncontrolled later on. So an unstable mill will not only give an instantaneous unstable flow to the burner, it will escalate the whole thing by having bigger settlement tendencies in the pipe. And these settlements later on will push into the burner completely uncontrolled. So getting your mills far more stable in output is a big target, because if you have fuel pulsations on the burner, you have immediately CO, you have immediately NOx, you have immediately all these problems, slagging. Better mill control is also a very big part of optimizing your combustion. Not only the imbalance between burners, but also the dynamic behavior of the flow to your burner is a big part of the controls. So that's an important part to optimize combustion.
Sure. Thank you very much for that, Hans, and thank you for the insight. So, just a quick reminder to the audience, if you did not get your questions answered, they can be answered at a later date. So that just leaves me to thank Hans for what a great presentation, and to PROMECON for sponsoring this event. Now, to all the attendees, you will receive an email shortly on how you can access the on-demand version, or you can access it at our website, which is www.business-review-webinars.com. We look forward to sharing future webinars with you, so please do keep an eye out on our website, as mentioned, and follow us on Twitter at BRWebinars for daily updates, and join our LinkedIn community group. Once again, thank you all very much for attending today's webinar with PROMECON, and hope you all have a very pleasant day. Thank you very much.
Thank you.